More than 4 centuries ago, in the distant year of 1610, Galileo Galilei made one of the greatest astronomical discoveries of his time. In his small telescope by modern standards, he saw 4 objects located close to Jupiter. One of them was called the Genius of the House and is currently considered the largest satellite in the entire solar system. The other 2, Europa and Callisto, according to the results of modern research, turned out to be promising candidates for the search for extraterrestrial life. The 4th satellite, located closest to the gas giant, was named Io. For a long time, technical limitations did not allow us to see the details of the surface of this celestial body, and its composition and internal structure remained a matter of guesswork. However, thanks to the development of science, astronomers received more and more information over time. It is now known that Io is one of the largest satellites in the entire solar system, second in size only to Titan and Callisto. Its radius is 3,821 kilometers, and its mass is approximately 8.9 by 10.2 kilograms. If we compare this celestial body with the Moon, it turns out that the sizes of these objects are almost identical to each other. However, if we compare their masses, we can see that Io is 21% more massive than the main satellite of our planet. This suggests that the average density of this space object is higher than that of any satellite in the solar system. According to calculations, it is about 3.5 grams per cubic centimeter, which is significantly more than most of these rocks. And to understand the reasons for Io's anomalous density, we need to look deep into its depths. According to modern ideas about the structure of celestial bodies, a relatively compact core of iron and sulfur is located in the center of Io. It contains about 20% of the satellite's entire mass, and the radius, according to various estimates, lies within the range of 350 to 900 kilometers. Calculations show that with such parameters of internal heat release will not be enough to melt most of the core. This is also confirmed by the almost complete absence of this celestial body's own magnetic field. Mathematical modeling shows that the satellite's core is surrounded by a solid mantle consisting of at least 75% magnesium and containing minerals of the forestreet. According to calculations, its outer part is molten and forms an ocean of magma about 50 kilometers deep. Its temperature is about 1600 Kelvin, which exceeds 1300 degrees Celsius. The deeper layers are under high pressure, which is why they remain solid even at significant temperatures. In turn, the mantle covered by the lithosphere, the thickness of which lies within the range of 12 to 40 kilometers. Despite its significant thickness, it is not monolithic. In some areas, the surface of the celestial body cracks, forming large faults filled with lava. At the same time, spectral analysis shows that, unlike most satellites, there is practically no water on Io ice and frozen gases. Basically, the outer surface of the celestial body consists of basalt and sulfur, but also has inclusions of other dense minerals. And it is precisely this fact that explains its abnormally high density. By the beginning of the 21st century, the surface of Io had been explored by at least 5 automatic orbital stations. However, The greatest amount of information was obtained in the 70s of the last 100th century during the Pioneer and Voyager programs. In the pictures transmitted by the probe to Earth, scientists discovered giant gas emissions, some of which reach water 500 kilometers away. This observation opened a new page in the study of the solar system for scientists. After all, previously active volcanoes were known only on Earth. For the first time, astronomers saw recently solidified lava flows, or volcanoes that went extinct 1 billion years ago outside their home planet. And active eruptions are even more impressive in some respects than on Earth. In general, about 400 active volcanoes were discovered on the surface of the satellite. That is, about 2.5 times less than on our planet. However, its area is significantly smaller than that of the Earth, which allows us to consider it the most active volcanic object in the solar system. It is not surprising that such an unusual celestial body attracted the close attention of astronomers. During the research missions, a number of photographs of different resolutions were accumulated, thanks to which in 2012, it was possible to compile a geological map of Io. Its quality allows you to see the largest relief forms of the celestial body, such as plains, mountain ranges, lava, flows, and of course, numerous volcanoes. And one of the most remarkable features is, of course, a huge orange-brown ring located in the southeastern part of the satellite. This vast area extends over 1,000 kilometers and is comparable in area to the large African side. It is thought to be formed by clear ejecta from the ancient volcano Pele, located at the center of the ring. Analysis of both infrared and visible light photographs show that the center of the ring is the loss of this volcano, which is a multi-level lava-filled depression measuring 30 by 20 kilometers. The temperature of the molten rock surface is unevenly distributed and constantly changes, reaching 1,300 degrees Celsius at the hottest points. It is assumed that the losses are connected with an underground channel with the hot mantle of the satellite. The lava inside the fault is constantly mixed because the volatile substances dissolved in it try to rise up, dragging the flow of molten rock with them. Because of this, the thin crust of solidified substance covering the surface of the lake cracks and breaks from time to time, giving rise to splashes and ejections of lava. Some of them can exceed the height of 300 kilometers, sending frozen particles of greystone straight into space. Gradually losing speed under the influence of gravity, volcanic sediments are scattered over the surface of the satellite, after which they smoothly descend. This is how a giant ring is formed, clearly visible from space. Many volcanoes of Io have similar formations, but the Pele ring is the largest of them. It is the active volcanoes that are the main reason for the formation of Io's unique atmosphere. According to available data, the satellite's gas shell is very dissolved and mainly consists of sulfur dioxide. At the same time, its density varies greatly depending on the region. For example, volcanic plumes. The gas pressure is 25 million times lower than on Earth. At the same time, far from the eruption, the atmospheric pressure on the day side of the celestial body is on average 1 billion times less than the value we are used to, and the night hemisphere of the satellite is almost in a complete vacuum. The density of the atmosphere there is 1 trillion times lower than on Earth. Also, despite the extreme resolution of the atmosphere and the absence of its own magnetic field, polar lights have been observed on Io. Charged cosmic particles, accelerating Jupiter's magnetospheres, bombard the close satellite, causing a multicolored glow of its atmosphere. At the same time, Io's polar lights, unlike those on Earth, most often occur at the equator, since it is there that particles flying along a tangential trajectory have to overcome the thickest layer of the atmosphere. Meanwhile, our journey across the expanses of Io will continue in a northwesterly direction. Having overcome the boundaries of the Opal landing ring, we will soon see the vast Basova mountain range. Its overall diameter is about 540 kilometers, and among other peaks, a giant peak called South Savala stands out. With dimensions of 145 by 159 kilometers at the base, this mountain rises above the average level of the satellite, more than 18 kilometers, which is twice as high as the Earth's Everest. The total area of the entire elevation is almost 18,000 square kilometers, which is comparable to the size of a small European country, for example, Montenegro or Slovenia. The appearance and structure of this relief form suggests that it arose as a result of a grand tectonic cataclysm. Probably in the distant past, a fragment of the satellite's elite sphere being formed, tilted and partially sank into the mantle, while one of its edges remained forever elevated above the surface. As a result, the southeastern slope of the mountain is a steep cliff about 15 kilometers high, making it one of the highest, second in the entire solar system. On Earth, such a formation is impossible due to higher gravity, and on other planets and satellites due to low tectonics activity. For this reason, South Savala can be considered a truly unique peak in the solar system and if we continue moving in a northwesterly direction, we will soon reach a giant abyss called the Loss of Laki. This formation is the largest volcanic depression on Io, with a diameter of about 250 kilometers. Thus, the total area of this grand failure exceeds 50,000 square kilometers, which is about 1.5 times larger than Lake Baikal, one of the most majestic lakes on our planet. However, unlike terrestrial reservoirs, this rift is not filled with water, but with hot, thorny silicate lava deep in the depths. Several dozen kilometers from the surface, this lava lake has a direct connection with the mantle, which serves as an inexhaustible source of molten matter for it. In a calm state, the surface temperature of which fluctuates from 270 to 313 Kelvin, which corresponds to a range from 3 to plus 57 degrees Celsius. Such a low value is a consequence of the fact that the upper layers of lava cool down, contacting with the permitted atmosphere of Io. As a result, they gradually solidify, forming a slowly growing solid crust, the mass of which reaches a critical value within 4 to 6 days. After that, it cracks under its own weight and sinks, causing flooding waves. They also overflow the surface of the lake at a speed of about 1 kilometer per day. Gradually, the lava lake calms down and again begins to be covered with a slowly solidified solid layer. Until the next flooding cycle, due to the almost complete absence of water and carbon dioxide on the surface, necessary to support life in our usual understanding. This celestial body is considered unfavorable for its genesis. However, the conditions on the surface of Patras, Loki, and other living lakes could hypothetically be suitable for the origin of unusual life. Resistant to high temperatures and receiving energy from chemical reactions involving sulfur or iron. Similar creatures also live on Earth, mainly in the craters of their underwater volcanoes or isolated ocean caves. However, due to the tectonic activity of Io and the extreme temperature differences on its surface, the probability of this phenomenon is quite low. Meanwhile, it can be noted that although the hills and volcanoes are the most notable forms of relief on Io, they occupy a relatively small area. Tectonic active areas of the surface are separated by large areas of relatively flat space, covered with a thick layer of clean sediments. When viewed from space, such regions are distinguished by a lighter color, and the largest of them extend for 1,000 kilometers. For example, if we go west from 1.5 Loki, passing many small volcanoes and frontal flows, we will soon reach an area called it is a light, relatively smooth space of irregular shape, surrounded by mountains and large losses. Its diameter, according to various estimates, is about 2,600 kilometers, and its area corresponds to about 12.60% of the entire surface of the satellite. Most of this region is uniform and smooth, but in some places the plain is cut by lava flows associated with adjacent volcanoes. It is assumed that only the sphere under the copper region has an increased thickness, forming a semblance of the Earth's continents, due to which such a large area of the surface retains integrity for a very long time. According to another hypothesis, the upper layers of the satellite's mantle melted fragmentarily and under tectonic inactive. Plains are absent, liquid magma. Observations show that, unlike volcanic regions, Io's plains are characterized by a cold climate. Thus, the temperature of a cloudy day does not differ significantly from the average value for the entire satellite and is only 110 Kelvin, or negative 163 degrees Celsius. That is, hundreds of degrees colder than in most volcanic regions 5 times. At this temperature, sulfur dioxide from atmospheric emissions settles as frost on the surface of the satellite, forming a smooth and even relief painted in hundreds of shades of yellow, red, and black. Be that as it may, future research will certainly bring us much more data about this region. Having overcome the smooth curves of the northern Midi Hills in the northwest direction, we will find another large depression known as Pomerania. Like most other volcanoes of the satellite, it is more of a celestial body filled with lava. Its diameter at its widest point reaches only 37 kilometers. However, when viewed from space, this volcano is almost as noticeable as the largest objects on the surface of Io. The fact is that it was previously surrounded by several giant flows of solidified lava, which stand out with their dark color against the background of the adjacent light plains. The largest of them goes north and extends for more than 300 kilometers, and its width reaches 60 kilometers. Thus, this relief form is the largest in the solar system. Active frontal flow. The second largest flow is lost in the western direction for a distance of about 250 kilometers. Previously considered a separate formation, but after receiving detailed images of the surface, it became clear that this object is also part of Pomerania. In addition, to the east of the main five, a crown of small dark flows departs, the color of which suggests that they consist of molten and subsequently solidified silicates. Pomerania has a complex internal structure. It is assumed that in addition to the main active region, additional magmas and pipes lie under the surface of the satellite in this region. Their periodic breakthroughs are the cause of eruptions outside the main trench. Observations in the infrared spectrum show that the main loss of the knee is approximately 2,900 Kelvin or 1,630 degrees Celsius, and the temperature of individual hotspots surrounding it reaches 1,200 Kelvin or 930 degrees Celsius. Such a high figure is probably due to the fact that directly under the volcano, there is an ascending magma and a flow bringing molten matter from the lower layers of the mantle. Also, the available data indicate that the early one is most likely a very young volcano. Over time, it will erupt, and the lava will form a vast flat shield with a diameter of hundreds of kilometers. And it is quite possible that this volcano will become similar to the Martian Olympus. It is difficult to argue with the fact that for its relatively small size, ESO exhibits extremely anomalous tectonic activity. After all, due to its low mass, it does not have sufficient reserves of radioactive substances, the decay of which is the source of internal heat for most planets. It is believed that the cause of the non-standard activity of this celestial body is tidal interactions with Jupiter in combination with orbital resonance, which maintains an unstable orbit. The attraction of the gas giant strongly heats the bowels of the satellite and also deforms its crust, which causes frequent and powerful eruptions in combination with low gravity. They become truly impressive. Giant emissions reach outer space, supporting scattered clouds of particles around the celestial body. Some of them fall back to Io. Others are accelerated by Jupiter's magnetic field bombardment, its sphere, and others settle on other satellites of the gas giant or replenish its rings. These are the kind of massive eruptions that are constantly occurring in a region called the Lost Ball, which is located in the northern part of Io. This region is a site of pronounced volcanic activity with a diameter of about 300 kilometers. According to available data, several volcanic quintets are located on its territory, presumably associated with a single underground source of lava. Over the past 3 decades, several powerful and prolonged eruptions have been recorded here. For example, in 1999 to 2000, the height of emissions reached 385 kilometers, and volcanoes' low precipitation covered the area of the surface with a radius of more than 700 kilometers. In addition, during this eruption, a gigantic amount of sulfur silicate lava splashed out 5 times and flooded a huge adjacent area. Several years later, in 2006, another large eruption began in the same area, which lasted 530 days, thus becoming the longest cataclysm in the entire history of Io observations. This time, the column of emissions rose to 330 kilometers, sending 1,000 tons of matter into space. It is obvious that the two spheres are a very active region from the point of view of tectonics, and the study of its emissions will allow obtaining a lot of data on the internal composition and structure of the satellite. It will not be an exaggeration to say that Io is a unique and very interesting celestial body, the study of which is still ongoing. In particular, on February 3, 2002, the orbital station Juno flew at an altitude of 1,500 kilometers above the surface of the satellite and transmitted many high-quality photographs to Earth. They show giant fractures of the celestial body, as well as volcanic plumes and lava flows. It is assumed that such flybys in the future will help to conduct a spectral analysis of Io's atmosphere in order to clarify its composition and parameters. However, despite the interest of astronomers in this celestial body, at the moment no specialized mission is planned to study it. The JUICE and Europa Clipper projects are focused on studying the honey of Europa and Callisto due to their potential unsuitability. And although at the beginning of the century, NASA specialists announced the development of a mission called an air show, the purpose of which was to be the volcanoes of Io, nevertheless, for a number of reasons, it was never implemented. Such unique cosmic objects as Io are born due to an incredible combination of many factors. Its majestic volcanoes and grandiose emissions amaze us even today, just as they did at the moment of their discovery. The opportunity to observe and study them is truly priceless. After all, every grain of scientific knowledge moves our civilization forward, and if even within the solar system we can discover so many amazing mysteries, then beyond its borders, in the vast expanses of the Milky Way, we are sure to find countless amazing discoveries. And we will hear each other.